Welcome back. Today we're wrapping up phase 1 of our series with a deep dive into transfer learning, one of the most important concepts in modern AI.
Transfer learning is really the secret sauce that makes foundation models so powerful and practical.
So, what exactly is transfer learning?
Transfer learning is the idea that knowledge gained while solving one problem can be applied to a different but related problem. Instead of learning everything from scratch, you transfer what you've learned.
Think about how humans learn. If you know how to play the piano, learning the organ is much easier because you transfer your knowledge of music theory, rhythm, and hand coordination.
In machine learning, transfer learning typically means taking a model trained on one task or dataset and adapting it to perform well on a different task or dataset.
For language models, this usually means pre training on a large general corpus and then fine tuning on a smaller task specific dataset.
Let's break down why this works. During pre training, the model learns general representations, understanding of language structure, common sense reasoning, factual knowledge, and so on.
These representations are useful for many downstream tasks. If the model understands grammar and context, that helps whether you're doing sentiment analysis, question answering, or summarization.
The key insight is that learning good general representations requires lots of data, but adapting those representations to a specific task requires much less data.
Let's talk about the main approaches to transfer learning. The most straightforward is full fine tuning.
In full fine tuning, you take your pre trained model and continue training it on your task specific data. All the parameters in the model are updated.
This works well when you have a reasonable amount of task specific data, say thousands or tens of thousands of examples.
But full fine tuning can be expensive because you need to store gradients and optimizer states for all parameters. For a model with billions of parameters, this requires a lot of memory.
It also risks catastrophic forgetting when fine tuning on a narrow task causes the model to lose its general capabilities.
Catastrophic forgetting happens because the parameters that encoded general knowledge get overwritten with task specific knowledge.
There are techniques to mitigate this, like using lower learning rates, training for fewer steps, or mixing in some general data during fine tuning.
Another approach is feature extraction, or using the model as a frozen encoder. You don't update the pre trained model at all, you just use it to create representations that you feed into a small task specific head.
This is very efficient because you only train a small number of new parameters, but it might not perform as well as fine tuning if your task is quite different from the pre training task.
A middle ground is parameter efficient fine tuning, or PEEFT. These are techniques that update only a small subset of the model's parameters while keeping most of them frozen.
We'll dive deep into PEEF methods in a later episode, but examples include adapters, prompt tuning, prefix tuning, and LoRa.
These methods can achieve performance close to full fine tuning while updating only 0.1% to 10% of the parameters.
Another form of transfer learning is few shot or in context learning. Here, you don't update the model at all.
Instead, you provide a few examples of your task in the prompt itself. The model learns to recognize the pattern and apply it to new inputs.
For example, you might show the model three examples of sentiment analysis, a positive review, a negative review, and a neutral one, and then give it a new review to classify.
Large models like GPT-3 and GPT-4 are surprisingly good at this. They can learn new tasks from just a handful of examples.
There's also zero shot learning, where you just describe the task in natural language without any examples.
For instance, you might say, translate the following sentence from English to French, and the model will attempt the translation even if it wasn't specifically fine tuned for translation.
The ability to do zero shot and few shot learning is called in context learning, and it's one of the most remarkable emergent capabilities of large language models.
Let's talk about domain adaptation, which is a specific type of transfer learning where you adapt a general model to a specialized domain.
For example, you might take a general language model and adapt it to medical text, legal documents, or scientific papers.
This typically involves continued pre training on domain specific text, followed by task specific fine tuning.
Continued pre training helps the model learn domain specific vocabulary, jargon, and reasoning patterns without losing its general capabilities.
You might train for a few more epochs on medical literature, for instance, before fine tuning on a specific medical task like diagnosis suggestion.
Another important concept is multitask learning, where you train a single model on multiple tasks simultaneously.
The idea is that learning multiple related tasks together can improve performance on all of them by finding shared representations.
T5 from Google is a great example. It was trained on a mixture of tasks, all framed as text to text problems, translation, summarization, question answering, and more.
This multitask pre training made T5 very versatile and good at generalizing to new tasks.
There's also curriculum learning, where you carefully order the training data from easier to harder examples.
Just like how we teach children simple concepts before complex ones, curriculum learning can help models learn more efficiently and reach better final performance.
Now, why does transfer learning work so well for language models specifically?
Language is fundamentally compositional. Complex meanings are built from simpler building blocks like words and phrases that combine according to grammatical rules.
This means that general language understanding is genuinely useful across many tasks. Understanding syntax, semantics, and pragmatics helps whether you're translating, summarizing, or answering questions.
Also, language models can store factual knowledge in their parameters. This knowledge, learned during pre training, is valuable for many downstream applications.
Transfer learning also enables rapid experimentation. You can try different task formulations, prompts, and approaches without retraining from scratch each time.
This has democratized AI development. Small teams and researchers without massive compute budgets can build state of the art applications by leveraging pre trained models.
Of course, transfer learning isn't perfect. The model might transfer biases from the pre training data. It might not adapt well if the target task is very different from anything seen during pre training.
And there are questions about when to use which approach. Should you fine tune or use in context learning? How much task specific data do you need? These depend on your specific situation.
But overall, transfer learning has been transformational. It's the reason we can build effective NLP systems for specialized tasks without needing billions of tokens of task specific training data.
So, to recap, transfer learning lets us reuse expensive pre trained models for new tasks. It can be done through fine tuning, feature extraction, parameter efficient methods, or in context learning, and it works because general language understanding transfers well across tasks.
This concludes phase 1 of our series on LLM foundations. We've covered what LLMs and foundation models are, the evolution of neural networks, transformers, training basics, and transfer learning.
Next episode, we're starting phase 2 on the core mechanics of LLMs. We'll dive into tokenization and embeddings, how text is actually represented for these models.
Thanks for staying with us through these foundational concepts.
Until next time, keep learning and stay curious about AI.